We have discussed the carbon cycle in many contexts, including, of course, decarbonization, net zero, and CO2 as the most prominent greenhouse gas, as well as methane. So we have to now also think about how the carbon cycle responds to global warming. So we are increasing greenhouse gases and CO2, methane, and they affect warming and everything else. And you expect those to affect the carbon cycle in return. Not all models always include the complete feedback cycle. We have enough uncertainties in doing the carbon cycle itself because if you think about the vegetation, the ocean circulation, and the biological pump in the ocean, the solubility pump in the ocean, we have discussed this elsewhere. CO2 dissolves easily into the ocean, so it is taken up and down by the circulation, upwelling, downwelling, and sinking, and so on, which we call the solubility pump. And then there is biology in the ocean, photosynthesis, and then up the food chain. And those also sink, move, migrate on daily time scale, and so on. So there is the biological pump. So this paper, very nice review from the annual, oops, I don't know why I moved it, but anyway, to put it in the display mode before I can bring up the pointer, by Dave Siegel and the group, very prominent scientists in marine biology, mostly satellite experts. So this paper has a lot of future suggestions or suggestions for the future of improving biological pump understanding and its carbon cycle impacts on global scales. So this is about quantifying the ocean's biological pump and its carbon cycle impacts on global scales, remembering that ocean takes up more than 90% of the additional energy we are trapping by increasing greenhouse gases, and it takes up about 25% of the CO2 we are putting out. So it's very critical. Plus, the warming, of course, reduces solubility, and then the circulation changes can also affect the ocean uptake, so sources and sinks, all these are very critical issues. So you want to have a good handle on how the carbon cycle will respond as the climate keeps warming and CO2 concentration in the atmosphere increases. It's of course there is always acidification, plus you're going to affect directly the deoxygenation, sea level rise, corals, biology, fish, disease pressure, and so on and so forth. So I'm going to be very brief. It's a nice long paper, a review paper, hence it has a very nice long list of references that you probably want to look into if you are interested in more details on this topic. So biological pump, carbon sequestration, satellite oceanography, biogeochemical modeling, ocean carbon cycle and carbon export pathways are discussed. So just look at the key figures and few final words. In the meantime, the abstract says the biological pump transports organic matter created by phytoplankton productivity in the well-lit surface ocean, we call the euphotic zone, to the ocean's dark interior, where it is consumed by animals and heterotrophic microbes and remineralized back into inorganic forms. So we are taking CO2, doing photosynthesis, producing food at the bottom of the food chain. The food chain then consumes it as small zooplankton, big zooplankton, small fish, big fish, and so on. And either it's all consumed in the euphoric zone or the heterotrophs move up and down and then life is there throughout the water column, even at the deep, dark, high pressure, cold bottom, right? This downward transport of organic matter sequesters carbon dioxide from exchange with the atmosphere on timescales of months to millennia, depending on where in the water column the respiration occurs. Respiration, of course, is the opposite of photosynthesis, where photosynthesis is producing energy and respiration is consuming that energy and producing CO2 in most cases. You have other processes by which methane can be produced as well, and so on, right? There are three primary export pathways that link the upper ocean to the interior: the gravitational, the drop, migrant, so things that move up and down like the zooplankton and the fish or whatever, and mixing pumps where the water itself is moving up and down and mixing nutrients and helping the biological pump and the carbon cycle. These pathways are regulated by vastly different mechanisms, making it challenging to quantify the impacts of the biological pump on the global carbon cycle. In this view, we assess the progress toward creating a global accounting of carbon export and sequestration via the biological pump and suggests a path towards achieving this goal. So it's kind of a perspective on where we need to go in the future and what data gaps are there, what new satellite technologies and what kind of accuracy and precision we need, and so on and so forth, which I won't read in detail. Some definitions always fun listening to because you are either not from the background or you have the background, but we just have to remind ourselves. Net primary fraction, of course, is the conversion rate of inorganic carbon to organic carbon by phytoplankton photosynthesis. So you're taking, CO2 and making hydrocarbon out of it, C6H12O6 or CH2O in a simple unit form. Sequestration, a process of isolating and storing respired CO2 within the ocean interior and mainly away from the exchanges with the atmosphere. Sorry, I already end up having this when I start recording. Dissolved inorganic carbon is the summed concentration of inorganic carbon, which is in the form of CO2, H2CO3, HCO3 minus, and CO3 minus minus, dissolved in the water that we've discussed elsewhere. Export flux is the transport of organic carbon from the surface ocean to the interior past a given depth horizon, typically the base of the euphoric zone. Euphoric zone, the depth range in the near surface ocean with enough sunlight for phytoplankton NPP to occur. Remember, light, sunlight is very critical for photosynthesis, right? CO2 plus H2O, but you need that HU. Remineralization, the conversion of organic matter back to inorganic forms by heterotrophic microbes and animals, because you need to constantly keep converting the organic matter back into nutrients for supplying to the photosynthesizers. Export pathways, the contribution to carbon export from the euphoric zone to gravitational sinking, animal migration, and mixing and circulation processes. Remote sensing, of course, all that satellite stuff that we talked about. Chlorophyll is the pigment that is required for photosynthesis. Inherent optical properties, IOP, the light absorption and scattering properties that are independent of the illumination conditions and are dependent upon the concentration and composition of dissolved and particulate materials and seawater. Things like quality of water, so there is levels and how murky it is and so on in terms of, this is very important to understand and interpret the satellite. Satellite is measuring radiances coming from the surface, and that depends on what the inherent optical properties are so that you know what you are actually looking at, right? LiDAR is an active remote sensing system that uses a collimated light source to quantify atmospheric and oceanic optical properties, light detection and ranging as opposed to radar. Export ratio, of course, is a measure of the export efficiency of the biological pump defined as the export flux divided by the net primary production. I won't look at the equations here. 234 thorium disequilibrium is the difference between the activity levels of 234 thorium 234, which is highly particle reactive, and those of its parents like uranium 238, which is not. It's not reactive. Its magnitude provides estimates of particle scavenging from the upper ocean, so it's kind of a tracer to diagnose certain things. So look at few figures. Food web diagram illustrating the three export pathways, euphoric zone food web, and the many ecological and biogeochemical processes regulating its relationship with the gravitational migrant and mixing pumps that transport organic carbon to depth. Beneath the euphoric zone, organic carbon is remineralized back to dissolved inorganic carbon via the food web processes in the mesopelagic zone. So you have epipelagic, mesopelagic, and bathypelagic, abyssopelagic, and so on. The depths to which the organic carbon is transported set the time scales of sequestration. So they don't drop always unless they're like a rock. So they often go, zigzagging down. So you have DIC, DOC, and POC. And here is the diagram. I have already shown this in the carbon cycle course, but you can look at it again. So here you have the euphoric zone and then the mesopelagic zone. This is where a lot of the respiration happens. So you have phytoplankton, and then they are grazed by zooplankton, which respire, and photosynthesizers themselves, of course, have to respire to produce energy. So you produce DIC, and then there is bacteria and DOC and POC. So there is the mixing pump, which is moving these material organic matter up and down. And there is sinking phytoplankton as well as disaggregation. So again, kind of a lot of processes that keep moving it into DOC and POC. And so you have biologic carbohydrate sugar type material that's converting to dissolved organic and particulate carbon and dissolved inorganic carbon after respiration and so on. So zooplankton themselves form pellets, detritus, fecal pellets, and so on. So sinking fecal pellets in carcasses, sinking aggregate. So that gives you the gravitational pump. And then you have the migrant pump where you have zooplankton and other things migrating up and down. They are up at night mostly because they want to avoid predation in the light zone, but that's where the food is. So they come down during the day and they go up during the night. So there is a massive movement of carbon because this can be tons and tons of organic matter moving up and down. And the sequestration times for DIC can be 1 to 10 years or 10 to 100 years, and then the migrant pump moves a certain amount. The paper provides numbers for each that I'm not going to read, but this pelagic zone, of course, has aggregate and fecal pellets that have come down. You have solubilization and disaggregation, again going into DOC and POC, consumption by zooplankton and respiration producing DIC. So here you have 100 to 1,000 years as opposed to 1 to 10 years. You have 10 to 100 years here at the let's say, interface of the euphoric and mesopelagic zone. Uh, and you have, of course, excretion, uptake by the bacteria, and respiration by the bacteria. So all these components matter. Satellite data-driven global export flux and sequestration estimates. I won't read all the numbers, but basically, you again look at gravitational pump, migrant pump, and mixing pump, and you look at F ratio. So you look at nitrogen 15 for new production, which we'll define in a minute. E ratio, export ratio. So depends on new production or total production, NPP, and the ratios. So you have sinking flux based on global summary of available observations, food web models, biogeochemical inverse models, where you take the data and see what constraints they place. So like if you just observe chlorophyll, does it can it be used to do inverse modeling to produce primary production and then export flux and so on and so forth. So food web model embedded in biogeochemical inverse model and migrant pump, you have food web model with migrant and flux remineralization. Mixing pump takes care of large scale subduction pump in biogeochemical inverse model. Subduction is technical term where the water masses are put away from the near surface layer into deeper layers. Everything you do in the ocean is about what the atmosphere sees and what gets hidden away. Okay, so subduction is one of those processes. Sorry for being brief, but all these numbers are nice. There are lots of uncertainties, and reading them off is not going to help you much anyways. Okay, so you want to look at the totals, and you want to take oxygen, budget, and circulation as the approaches to do the totals and constrain them, especially the inverse models. In the forward models, you are modeling everything. You're modeling nutrients, circulation, phytoplankton, zooplankton, grazing, and some predation rate, and so on. Models typically don't do beyond zooplankton, even though there are fish models, of course, species specific, or sometimes they are uh, total predator population, prey population, and so on and so forth. Okay, so that's what food web model embedded in a biogeochemical inverse model means. So what do they do? Export from the euphoric zone, and then there are numbers that are estimated from those. The second figure looks at the accumulation of uncertainty from top of the atmosphere radiance to the irradiance at the surface, how it gets into particulate organic carbon, intrinsic optical properties, chlorophyll. Of course, there is sea surface temperature with the air-sea interactions, circulation, coupled modes, which is going into these various boxes to produce net primary production. And then you have food web models or empirical models or inverse models that we talked about that either use or rely on in situ oxygen and nutrient data. In the full models, food web models, you are often computing everything, including oxygen, but eventually everybody is trying to estimate carbon export and sequestration. If it falls out of the euphoric zone, it's exported and not available for recycling and consumption, but it may get recycled into inorganic matter. But sequestration means it made it out of the system, let's say, to the bottom of the ocean. So ocean circulation, of course, has to be taken care of as well. Okay, so some data here, comparisons of satellite products for phytoplankton carbon and net primary production. You can see that milligram carbon per meter cube in phytoplankton. You can see interannual variability from 2007 to 2015 or so. And here you see the pattern, upwelling, spring blooms here. Southern Ocean is a combination of spring blooms and many other processes. And Indian Ocean is different than the other two tropical oceans. Atlantic looks much more like the Pacific. There are also other details about how the dusts from Sahara will induce iron fertilization and so on and so forth. But you can see that two types of data are offering very different kinds of variability and numbers. This is going up and down, strong interannual variability, uh, but here it's a much smaller range. And here is CAFE, and VGPM is vegetation model and another model. So basically the point is that there are a lot of uncertainties, and you can see this is NPP estimates here. These are, so that's NPP in milligrams carbon per meters cube per meter squared, sorry, per day. This is just what is standing stock in milligrams of carbon per meter cube. So you can see the patterns here. Obviously, there is a lot of close relationship between uh, phytoplankton carbon versus net primary production, as you expect, right? But you can see the differences here in the Indian Ocean. So export versus net primary production and nutrient availability. There are many details like nitrogen limitation and what other iron limitation and so on and so forth. Okay, I'm being very brief, but you can follow up. Okay, so this is the export ratio again. You can see different papers produce remarkably different numbers. This is going to tell you just how different methods can yield different results and how this can induce all kinds of uncertainty into the carbon cycle and its response to warming, let alone what's happening now. And you can also think of the using data assimilation. So inverse models are where you're just using data. Data assimilation is where you're taking something like a circulation model. You're taking the data that's available and trying to merge dynamically and biogeochemically the data and the models to produce better estimates of the quantities that you want to worry about. So N15 uptake is used for new production. Nekton, of course, means those that can swim and move independently as opposed to plankton, which drift. And mesozooplankton are herbivorous and carnivorous animals with body sizes between zero point 0.2 and 20 millimeters. Some mesozooplankton migrate vertically. So what is the point about assessing carbon sequestration by the biological pump? This is what you are most worried about, because how much is the ocean taking up as a whole? Where are the sources? Where are the sinks? What's happening because of the warming, acidification, and nutrient pollution and other things, and how they are changing? What is their role in sequestering carbon right now, and what's expected to happen as global uh, warming and increasing greenhouse gases continue, right? So quantifying export is not sufficient to deduce the impact of the biological pump on atmospheric CO2 concentrations because the total strength of the biological pump depends not only on carbon export but also on the sequestration time of the exported carbon within the ocean. How long will it stay there? 1 year, 2 years, 100 years, 1,000 years, right? The sequestration time of exported carbon depends on where the exported carbon is aspired back to CO2 and how quickly the ocean currents transport the resulting dissolved inorganic carbon back to the surface where it can interact with the atmosphere and also change the uptake by the ocean because that's going to affect the chemical reactions with the background concentration. Generally, deeper remineralization supports increased sequestration times and greater efficiency of the biological pump. Thus, the total amount of respired DIC that is sequestered in the ocean depends on the remineralization of carbon in the interior ocean and its pathway back to the surface, aspects of which are explored below. I am not including those discussions here, but you can see how the different estimates of the gravitational pump, migrant pump, and mixing pump are estimated for the respiration rate in millimoles of carbon per meter cube per year. Okay, so that's the total, which is almost entirely dominated by the gravitational pump. And here you have the mean sequestration time from 0 to 1500 years. Again, uh, the different oceans have. So because Atlantic has a deep water formation, it is not that old. Sequestration is, I mean, newer production is coming down and sequestration time is affected by the circulation itself. And globally, we are here, which is again mostly dominated by the Pacific sequestration time because Pacific has some of the oldest waters. If there is a lot of production near the surface, that means the old waters are staying there, carbon is staying there, sequestration time is longer. Carbon sequestration in amounts, obviously, a lot of it happens in the oxygen minimum zone where maximum respiration happens. And here again, you have gravitational pump being the dominant one for the total in terms of carbon sequestration, which is consistent with this, even though these are inter-ocean differences. So you get a sense that very little gets to the bottom. If you look at the numbers in terms of paragram carbon per meter, you see that most of it gets recycled back here and very little drops below about 1 kilometer and makes it to the bottom. So by the time you reach the bottom, you have barely 0.1, 0.01% dropping, and that of course depends on where you are measuring them. What are the future directions? Much progress has been made in improving our abilities to observe and model the biological pump over the past several decades. As detailed here, the diverse pathways that make up the biological pump have been elucidated and their contributions have been diagnosed. Novel in situ and remote sensing observational tools have been developed and deployed, and large field programs are being conducted to observe and qualify the export pathways. Likewise, the data assimilated modeling systems have been developed to assess the different export pathways and provide estimates of the sequestration inventories. Intuitively, you can see just how difficult this problem is, right? So you look at the ocean, which covers so much of the Earth's surface, and then you have production below the surface, as you can see here, right? Respiration happening somewhere and export and sequestration time and so on. So everything is very local. Even if you go to the most productive regions, let's say we look at this one. Let's say this is one of the most productive open ocean region. These are essentially the deserts of the ocean, but there is subsurface production because enough light comes in and enough nutrients are available below the surface. And of course, the animals can move up and down in water as well. Things like big-eyed tuna can dive pretty deep, and there are many other animals like whales which dive pretty deep as well. So obviously complicated problem in terms of temporal scales at which these things happen and spatial scales at which these things happen. So through these developments, though, the field now appears close to realizing the critical goal of real-time monitoring of the biological pump at global scales. An operational system that can diagnose year-to-year and multi-decadal changes in the global biological pump will be crucial for monitoring the impacts of climate change and atmospheric CO2 removal solutions on ocean carbon export and sequestration. So there are all these podcasts I have on ocean as climate solution, ocean carbon dioxide removal, alkalinity enhancement, ion fertilization, artificial upwelling, and all those nice things. One compelling approach would be to develop a data simulated modeling system that synthesizes satellite and in situ data within physical biogeochemical models. Remember, satellite only sees the top few centimeters. If the waters are clear, it'll see deeper, tens of meters, but it's still seeing very little part of the deep ocean, right? So the components of such a system, one that diagnoses the export pathways and their contributions to water column remineralization and assesses the circulation, mixing, and gas exchange processes that link remineralized CO2 back to the atmosphere exist today, but all need improvement to reduce uncertainties in their combined assessments of the state of the biological pump. There are lots of details on new satellite technologies needed, what is expected, how accurate and how much better they will be, and so on. For example, will they only see chlorophyll or will they also see phytoplankton versus zooplankton, small phytoplankton versus large phytoplankton, and so on. Just to jump to the end, a final critical component of any biological pump monitoring system is accurate models of ocean circulation and mixing. These models also are needed to assess carbon sequestration timescales and to monitor changes in the inventory of sequestered carbon in the ocean. We want to see how long it stays and how deep it goes and whether it sinks out of to the bottom. The inverse models of the biological pump highlighted here, so you can read these papers, employ the steady state ocean circulation inverse circulation model because when you are taking data and trying to interpret what is implied in terms of export or E ratio, F ratio, and so on, you have to assume that it's giving you a sense of steady state. It's very hard to derive variability and trends from inverse models unless you do different chunks of time. Often you don't have enough time, enough of a sample, right? Time series is short. This model is computationally efficient and is effective at quantifying the climatological mean state of the carbon sequestration, but it cannot resolve temporal changes in ocean circulation. Recent advances have removed some of the constraints of the steady state assumption, and seasonally varying circulation fields have been created, but intra-annual and longer time scale variability remains unresolved. So you may do seasonal variability, but it's important, but you need much more. Other assimilation systems, such as the estimating the climate and circulation of the ocean echo approach, can better resolve intra-annual to decadal variability in ocean circulation and biochemistry. This is run either out of JPL or out of Germany in Detlef Stammer's group. There to see which one is being discussed here. But these suffer from incomplete spin-up and uncertainties in their deep ocean circulation. Further improvements in these data simulated ocean circulation models are needed in order to best quantify ocean carbon sequestration. Well, it's a nice topic. Sorry, I have to kind of rush it, but that's because I'm just trying to introduce you to the topic, and this is already 30 minutes. I should have split it into two, but it's okay. If you are interested in it, you will listen to it, and it's useful to read the paper and the tremendous list of references that are very useful as well. Okay? Enjoy either way. See you in the next topic.